going to do some extra examples from section 2.4. So we have the definition here, precise definition of a limit, and this is provided for you. Number 1 says, use a precise definition of a limit to determine the delta in terms of epsilon that will ensure that the limit as x goes to -4 of 1 minus 3/2 x is 7. Alright, so what I suggest you do is start with the very last part of the definition and write down the absolute value of f of x minus L. The absolute value of that is less than epsilon. And then plug in the things that are specific to this problem. So our f of x is 1 minus 3/2 x. Our L is 7. So this is going to be minus 7. And we have that less than epsilon. And then what we're going to try to do is we're trying to get the x minus a absolute value part on the left side. Our x minus a in this problem is x minus -4, which we might as well just go ahead and simplify to x plus 4. Once we get that on the left, then whatever is left over on the right hand side is what we want to let our delta equal, and it'll be a function of epsilon. So let's get back to the algebra here. There's some simple things that can be done with regards to simplifying. So -3/2 x, and then combine the 1 minus 7 to get -6. Okay, next thing to notice is that for the absolute value of x minus a, that the coefficient of x is always 1. So that means whatever, if anything, is in front of the x, and what we have over here, -3/2 in this case, that's the thing that you need to factor out. So I'm going to go ahead and get ready to do that. It's easy on the first term, but maybe you want to think about what the second term would be. So if I have plus a -3/2, you have to ask yourself, how do I get a -6 out of that? Because it has to be equivalent to that, so I'm going to have to times by something so that it equals 6. So different ways you can do that. You can even make a little equation here. Multiply by -2/3, and you get that that value would have to be 4. So now I'm going to actually factor out the -4, or just kidding, the -3/2. And I am left with x plus 4, which is really good news, because once I take away, get rid of the -3/2, that's what I'm going to want left behind. So here's something that you need to be a little bit careful here, that when you factor out the -3/2 out of the absolute value, it becomes positive. Take the absolute value of it. And now all that's left to do is to multiply both sides by 2/3. And we've achieved our goal of getting absolute value of x plus 4 on the left. We let our delta equal what's on the right, and that is the largest delta possible, which is the one we usually write down, in terms of epsilon. Let's go to the next example. This is actually one of your suggested problems. It says, use the given graph of f of x equals square root of x to find a number delta such that if the absolute value of x minus 4 is less than delta, then the absolute value of square root of x minus 2 is less than 0.4. Now this is really similar to the second example I did in class, but it's just a little bit of a twist here and there. and it's presented in a little bit different way. We pretty much do the same thing here. We're trying to find the delta, and we're not given an epsilon directly, but if you notice, we're given it implicitly. It's right here. So if you go to the notation from the precise definition, the generic form is the absolute value f of x minus L is less than epsilon. So you just have to match that up, that actually the epsilon is given at 0.4. Another place that you could figure that out is from the graph. Okay, so the next thing is we're trying to find the distance from 4 in the horizontal direction that will map us back up to within epsilon of 0.4. It's pretty obvious from this graph that we're going to need to do this only on the left, because finding the difference between 4 and this question mark right here on the right is going to get us a bigger value. And we find, or use the delta that's the smaller of the two. I'm just going to find all of them in case it's not obvious, and just to kind of show what you would do and kind of convince you that. So let's get going here. This y coordinate is 2.4, but we're trying to figure out the x coordinate. And we can do that because we have the function square root of x equal to that, and we just solve for x. So if you square both sides, what you get is 5.76. So that x is 5.76. Alright, so one candidate for delta would be the difference between that x value and 4, the place where we're taking the limit. So we get 1.76. Alright, let's do the same kind of thing for the y of 1.6. 1.6 is equal to the square root of x, and we get that x is equal to 2.56. So now to figure out what the delta is on the right, left, the delta on the left is where we're at. That's going to be 4 minus 2.56. Do that calculation and get 1.44. So we're going to take the smaller of the two. Some fancy notation here for that is, oops, not that. Delta equals the minimum of the right one and left one, or 1.44 and 1.76, which is 1.44. So delta is equal to 1.44. And that's it. The last problem is similar to the application of precision, but I organized it a little bit different. The cross-sectional area of a piston is allowed to vary between 2.9686 and 7.1686 square inches. The ideal area for the piston is 7.0686 inches squared. The ideal radius we want to manufacture for the piston is 1.5 inches. So we have a lot of information there. And the first thing says identify this stuff. So we have the limit as r goes to a of f of r equals L. What's already substituted in here for us is, instead of having the independent variable of x, we have the independent variable r as our input. So that's something to note. Now A is where we're taking the limit, which is our value. And so this is our ideal radius that we want. So let's go back and see what that is. It's 1.5 inches. And you don't really need the units here, but I wrote it down anyway. Okay, next thing, what is f of r? Or what's the output that depends on r? It's the cross-sectional area of a piston, and I should have told you that it is a cylindrical piston. I did that in the notes for the similar example, but I didn't do here. So let me just correct that quick. The cross-sectional area of a cylindrical piston. Okay. That's helpful to know that the cross-sectional area is a circle. Okay. Moving on, we have L. So that would be like the ideal output we want. Our output is area, cross-sectional area. And so we were told that that would be 7.0686. Alright, we got everything. So we can move on. Inches squared, I can put that in there. I don't really care if you do or don't. Next one. What is epsilon from the precise definition of a limit? Okay. So one of the things to remember is epsilon goes with the y stuff. And both epsilon and delta have to do with kind of like error stuff. The epsilon is like the error that's allowed for the output or the cross-sectional area. The y stuff, the output. So we're given some information about how much the cross-sectional area can vary between, and from that we can figure out exactly what the error tolerance is. So let's write it out. We know that 6.9686 is the lowest cross-sectional area we can have. And the highest is 7.1686. So up above, note that the cross-sectional area as a function of r is pi r squared. Now we can get to epsilon if we do a bit of algebra to repackage this thing up as f of r minus L in absolute values, because the other side would be epsilon. So we identified L in the part A as 7.0686. So what we can do here is we can just go ahead and subtract 7.0686 from all three places in this compound inequality. So that's what I'm showing here. And so on the very far left here, what we'd get is negative 0.1. I'm just going to use this generic form that it's f of r minus 7.0686 for now. And that in turn is less than the difference of these values, which is 0.1. So because these numbers are the same, 0.1 and negative 0.1 in terms of magnitude, that's really nice, because then we can go ahead and repackage it up in this absolute value thing. And so this will always work for finding epsilon, because that difference will be the same. So, kind of running out of room here, but the punchline there is that epsilon is equal to 0.1. Alright. Oops. I did this, I made this generic all here to save space, but there we go. Next part, find the range of values the radius r can vary. So we were told how much the cross-sectional area could vary, and we can use that to figure out how much the radius can vary. So I'm going to start back to where we started in part B. I'm going to actually use the pi times r squared, plug that in, and then you can see that we have a function in terms of r. So I can solve for r. I'm going to divide by pi. In this problem we're told to round to 4 decimal places throughout. I don't have you do sig figs. You'll do that in chemistry. So just 4 decimal places. We'll just go with that. So we're on the same page. So when I divide by pi, I get 2.2182 to 4 places. R squared is in the center, and then I get 2.2818 on the right. Final step, square root everything, and we get 1.4894 on the left, 1.5106. And this is an acceptable answer for this question. This is showing like, kind of like you can think of it, the domain of R, or the input, what it can be. It can vary between these two numbers. Finally, what is the error tolerance of the radius, given the ideal radius is 1.5 inches? In other words, what is delta from the precise definition of limit? Okay, we're really close to that actually. What we have in the precise definition is x minus a is less than delta. So for this problem, our x is like r. So we have r minus, and then our ideal radius is 1.5. It's less than delta. So what that means is we almost have that in our inequality where we left off in part C. So I'm going to write that down. I'm going to minus 1.5 everything to make it look like this a little bit more. And then what I get on the left is negative 0.0106 is less than, we have r minus 1.5, less than 0.0106. So if we're lucky, these things are equal in magnitude, which they are. If you're remembering what I said in lecture, we actually expected these values to be different magnitude because we have a nonlinear function. The reason it didn't happen here is because I had you overround to a point where you couldn't see the difference, which is alright. So I'm just going to write a little thing here about that. Expect to see slightly different magnitude numbers here. But you can't see because of the rounding. Put it that way. Alright, so that's just in case you're like, what? Why is that? Alright, so if these were slightly different, you would take the absolute values of them and then take the smaller of the two. And that corresponds to the graphical thing that we were doing in the example 2 on this worksheet. So you would just take the absolute values of these, take the minimum, and that's what you'd use for delta. So, but this one was a little bit easier, so we can go ahead and actually finish out the algebra like this, similar to how we found epsilon in this case. And our delta is equal to 0.0106. And that's it. Thank you for listening.